copy.
Okay, perfect. Thank you so much. So, para empezar con los tubos de fuselaje. I'm gonna switch cameras, okay?
Okay. Okay.
So, hi, this is Jose Luis. I'm from the Aerostructures team. I'm going to be, well, of course, it's a pleasure to meet you guys today. I'm going to be, well, pretty much describing a little bit of the rocket that we have been constructing and working on for the past couple of months. So, basically, we're going to be, this time, we're not going to be using UT or Anakin. We're going to be making, or we made the rocket of carbon fiber. And well, the length of the rocket is going to be for 302 centimeters. The weight is going to be for 26.2 kilograms. And of course, the airframe diameter is going to be for 6.7 inches. We're trying to reach an apogee of 10,000 feet. So
Okay.
I'm beginning to pretty much describe each one of the tubes. We're going to be beginning with the lower tube, which is for, it has a height of 37.4 inches. We're going to be pretty much connecting the fins and we'll, of course, putting the motor tube inside of it. Also, well, for the next one, it's the middle tube, which is the one that we're going to be using for the payload items or the payload support. Its height is for 27.6 inches. And lastly, we're going to be going with the upper tube, which is the one that we're going to be using for the control and recovery systems. This one has a height of 31.5 inches. And I forgot to mention that each one of these has a thickness of 0.12 inches. Also, here is our motor tube as well. It's pretty much the one that we're going to be using in order to support the motor. It's made of fiberglass and epoxy resin matrix. This one has a height of 24.8 inches and also a thickness of 0.12 inches. So we pretty much made each one of these tubs. Well, in this case, the ones for carbon fiber, we use carbon fiber, the 3K1. We did like the hand process, I think it's called, and we'll pretty much use the epoxy resin all over it. We did 3 layers of each one or the carbon fiber. And of course, for the upper tube, which is the one for the control and recovery, we pretty much use fiberglass. For this one, we use 2 layers of fiber. And for the one or for the motor tube, we also use fiberglass as well. For this one, I think we use three layers of it, and also the epoxy resin. So
Okay.
now I'm gonna be describing you guys how the furnaces are made. In this case, we pretty much use jute and carbon fiber. The fiber that we use for this case was the carbon fiber 12 case. They are pretty much attached in a 45-degree disposition. And well, that's about it. We pretty much did like 6 layers of them. We're gonna be using on the middle or on the center the carbon fiber 12K1, and at the very end of it, or like at the exterior of it, we're gonna be using the jute fibers. So how this is gonna work? Well, we're gonna be pretty much put the fins on the motor tube. We're gonna be making the connection this way. In order to pretty much attach them, we're gonna be using the epoxy glue and also a layer of fiber glass. And well, we're gonna be using 4 fins, of course, which we're gonna be putting them like all over this surface. And well, that's how we plan to pretty much do to pretty much use or install the fins on the motor tube. So,
Okay.
So now I'm gonna be talking about the nose cone, which it has a length of 27.6 inches. We're gonna be, well, it was made of jute and fiberglass fibers. And also we use the marine fiber inside of it. I think probably you guys can't really see it, but it's over here. In this case, the way that we pretty much manufacture this one is that we use well, we pretty much make half of it and half of the other one. And we, at the end, once we got the two parts of the nose cone, we pretty much put them together and we paste them, or we attach them with epoxy glue. And well, we also, I forgot to mention, so in order to make this one like that, to be the exact same weight measurements, we use a 3D printed PLA mold, just to be sure that it's gonna be, or that they are gonna be having the exact same measurements. We are gonna be using also this little tip, which is made from an aluminum 6061 alloy, and this is gonna be just to pretty much like
It's going to be glued at the top.
it's gonna be glued at the top with epoxy resin as well.
Okay. Do you plan to use to put a shoulder in the nose cone?
Oh, the reason why we cannot see the shoulder on the nose cone is because actually we're going to be using a coupler that's going to be attached at the bottom of the nose cone. It's going to be made out of carbon fiber, the coupler, and it's going to be attached to the upper tube.
Okay, and the nose cone deploys in the recovery of the rocket, or is attached with the rocket?
Well, yes, the nose cone is going to be deployed at the.
Lo menciona recuperación.
We're gonna talk about the process of the deployment of the nose cone a little bit further. I don't know if that's a problem.
Okay, what is the leg of the shoulder of the
The length
Nose
of the
cone.
shoulder is 1.2 times the diameter of the body tube.
Okay, thanks. The nose cone, do you plan to put anything inside the nose cone in the launch, or is empty?
We're gonna be pretty much putting the GPS model inside of it. That's what we plan to use. Here we have it.
Okay, and do you have any structural for the GPS? Who is the GPS insert into the nose cone?
Vamos a integrar el GPS en la ojiva.
Es con un rack, pero está en proceso.
We are building a rack structure that is
Okay.
going to be inside the nose cone, but it's still on fabrication. We don't have it with us right now.
Okay. And what is the plan to turn on the GPS? Do you have external switch to turn on the GPS in the launch pad, or do you need to take out the nose cone to turn on the GPS?
Switches on. Yes, we have an external switch to turn on the GPS.
Okay. Okay, thanks. And for body tubes, I already see the material, the leg. Do you plan to set the team name, team number, and the frequency of the
Sure.
signal? Okay.
Yes, it's just that we still don't have the stickers
Uh-huh.
with the team number and the frequency, but we're gonna put it on the body tubes.
Okay, and that body tubes has already the venting holes.
Come again? I'm sorry, I didn't quite catch that.
The body tubes already has the holes to prevent any premature ejection.
Okay, the bend holes.
Yeah.
We need to put it on them, but we haven't drilled the holes on the body tubes.
Okay. And now about the couplers. How many couplers? What is the material of that couplers and the leg?
Sure.
And which one do you plan to attach? Use chemical or maybe a mechanical attachment?
Sure. So, well, in this case, we're gonna be using 3 couplers. There is gonna be this one for carbon fiber, which is the one that we're gonna be using to connect the upper tube with the nose cone.
Mhm.
We plan to, well, make sure that they're attached by using M5 Allen screws and also some sharpins all over the surface. And we also plan, we're gonna be using the 2 other couplers. Oh, I forgot the measurement. So the one for carbon fiber is for 9.8 inches. And of course, we're gonna be using as well the one for, well, the other 2, which are the ones made on their fiberglass. In this case, there's gonna be this one. There's gonna be the one attaching the lower tube with the middle tube, and also the one that is gonna be attaching the middle tube with the upper tube, right? We also plan to pretty much use the exact same way of attachment. We're gonna be using the M5 Allen screws. And also, we're gonna be using the sharpins in order to make sure that everything is gonna be like that.
Okay. And which one of that copper used for the avionics is from? What is the material? Is fiberglass?
Are you talking about the material, the coupler, or the body tube?
The material of the avionics bay.
The
The coupler that you use to the avionics of your rocket.
So it's gonna be for carbon fiber.
Okay. And where in that tube do you plan to insert? My question is between you use coupler from fiberglass and then insert that fiberglass to carbon fiber tube.
La transferencia de datos.
The interference. It's due to the interference of the components that we're going to be using.
Okay.
Is that what you asked? Sorry.
Yeah, I just want to be sure that the signal of your GPS, GPS is in the nose cone, but maybe if you have a telemetry in the avionics.
At the avionics, we're not having any telemetry. We're going to have an inner payload.
Okay.
Yes.
Okay, perfect. Thank you. Now, can you tell me more about the fin section? You cut the slots for the fins in the fin can in the body tube.
Oh, sure. So in this case, once we pretty much put the fins all over the surface on the motor tube, we're gonna be pretty much using the. No. So we're gonna be using the epoxy glue and also the fiberglass in order to make the attachments. Once we have them, we're gonna be drilling a hole on the body tube in order to pretty much make the connection. And once we have that hole or those 4 holes, we're gonna be joining the lower tube is gonna be joining the motor tube. And of course, how are we gonna be assuring this? We're gonna be using another layer of carbon fiber, 12K, and some epoxy resin as well. Once we have that process made, we're gonna be working with the tip-to-tip on each one of the fins, just to be double sure that everything is gonna be secure.
Okay. Do you plan to cut the slots for the fins in the body tube to the end, and then insert all the body tube with the center rings and fins, and attach maybe with a screw? Because I see in the center rings a holes for screws.
Yes. So what we're going to be doing is that we're going to cut the slots on this body tube, which is the lower one, so that we can insert the fins, and then the fins are going to be attached at this body tube. And we're going to place fiberglass with epoxy resin, and also at the outside, it's going to have. It's going to have an extra layer of fiberglass, and with the tip-to-tip method.
Okay, but that assemble, what is the method that you use to attach with the body tube? You use a chemical like epoxy to attach The body tube with the fins, nose.
So the attachment of the motor tube with the body tube, or the attachment of the fins with the body tube?
No, all the assemble of the body tube with the fins, center rims, and the body tube. I see a little
You're talking about this holes,
holes.
right? Chris?
Yeah.
Okay, these ones are, well, we're gonna use screws to attach the body tubes with the motor tube.
Okay. How many screws do you plan to use? What is the material of the screws?
Pero, o sea, para cada anillo, we are using 4 holes or 4 screws per centering ring, and the material of the screws is stainless steel.
Okay. 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 Thanks for that information.
Okay.
Okay. In the competition, just be sure some member of your team need to flex the pins. Just for be sure that they have a good attachment with the all assemble.
Yeah, actually, we are planning to also make a test prior to the competition, just to test the flexion on the fins, just to make sure that, well, they do not present any flexion, so that we can confirm that those are rigid enough.
Okay. Now about the fin flare, what is the max velocity of the fin flare calculation, and what is the max velocity of your rocket?
Okay, so the film floater analysis that we ran, we actually did 2 different ones. The first one, we performed it with MATLAB calculation, and the other one was with ANSYS. And the result that we got is that the film floater velocity is 402 meters per second, and our maximum rocket velocity is 301 meters per second. So that gives us a margin of 33.7. I mean, we are 33.7% below the fin flutter speed.
Okay. Okay, thank you. About the motor retainer, what method do you plan to use for the motor retainer?
So the motor retainer, we're going to be using a Cox motor, and we are planning to place the truss plate at the bottom of the motor tube, and it's going to be attached to the motor tube and also to the airframe.
Okay, can you insert the casing into the motor tube?
Yes, of course. Just to let you know that this is not the casing that we're going to be using. This is for an M1845 motor, and we're going to be using M1939. It's a little bit longer, but the diameter is the same.
Okay, and the last center ring has the same holes?
Yes, it has the same holes as the other 2.
Okay. My question about that is the motor retainer has holes for the screws to attach to the center ring. Do you have enough area in the center ring to attach the motor retainer?
Okay, so you are asking about to insert the truss plate to this center ring?
The motor retainer.
The truss plate?
No, the motor retainer. That red motor retainer.
Okay.
They have how many holes for attach they have?
It has 3 holes. 3 holes.
Okay. Okay, yeah. No problem. I already see the area that you insert.
Yes.
Okay, thank you. Now about the effective rail leg. What is the velocity of your launch when you leave the rail of the launch pad?
So one of the issues that we have when we were designing the rocket is that our exit velocity is 26.6 meters per second, and we were told that we needed to prove that the rocket's going to have enough stability at while it's leaving the rail. So we perform several tests at different wind speeds so that we can determine that the stability of the rocket is enough to at the end of the rail.
Okay, and another question about that. What is the leg of the rail that you insert in the simulation? Because if you insert maybe 17 feet or the end of the rail between the first rail bottom.
So the length that we use for the rail is 5.2 meters, which is the one that ESRA provides.
Okay.
Okay.
And do you plan to use a boat tail in the
No,
rocket?
this year we're not using a boat tail. We did a drag analysis to see if it was worth it to manufacture it, and we found out that it was not. I mean, the reduction of the drag of the rocket using the boat tail, it was not so big if we did not use it. So that's why we decided to not use the boat tail this year.
Okay, no problem. Now about the rail bottoms. Do you have already the rail bottoms, and where in the rocket do you plan to attach
Yeah,
these components?
we already have the rail bottoms. Let me show you.
So yeah, they're gonna be like separate between them by 19.3 inches, and they're gonna be like from lower to the top. It's gonna be like 10.2 inches of height. So yeah, but we already have them. We just haven't put them in yet.
Okay. Okay, thanks. And now we can pass with the recovery subsystem. Where are the hard points in the rocket? Okay.
Hi, my name is Audrey, and I'm from the Recovery and Control System. Well, our recovery and control system is based on a double event pyrotechnical system. We will use a foundry charge that will be activated by igniters that will be connected with quick connectors. They will be located at the top and at the bottom of the rack. For our apogee at 10 feet, we will release our drop parachute. Our drop parachute was designed completely by our team according to the standards of the AAA Association. Then at 1,015 feet, we will release the main parachute, which is right here. Well, according to our calculations, we will have a descent velocity of 28.5 meters per second. And then theoretically, with our main parachute, we will have a descent speed of 7 meters per second. For the parachute, the shock lines are right here. We will have a length of 3 and 7 meters. We will use the daisy chain technique to integrate it to the rocket. We also have 2 flight computers that we will develop at SRAD computer, and we have this RRC3 Plus commercial flight computer that will be explained in a bit.
For the rack, we have discs. They are made of high aluminum, and we have 3 plates. It has a triangle form. So that plates are made are designed like the spider web. We made that for the structure to have a good way to allowing the forces to be spread. And the disc has a diameter has a holes that has a one fraction 8-inch diameter, and then we will have This design copies the shape of a spider web and allowing the forces to be spread in a good way. The cylindrical structure is inspired by geometry, and the rack that is manufactured from high-grade aluminum is are mounted on the recovery rack using screws that are in the holes.
Okay.
Do you have any questions?
About the material of the parachutes.
Yes.
Nylon.
This is this is made of nylon.
Ripstop nylon.
Ball parachutes have the same material.
Yes.
Okay, and for the shot core, what is the material? Sorry, the material for the shot core.
It's shredded nylon is the material.
Okay. What is the size? The size of the thread? Nylon?
0.37 meters.
3.17 meters, the length of the shot cord.
Okay. Now about the recovery system, what is the leg between all the components? I just wanna be sure that the components don't hit during the descent of the rocket. Do you have any diagram about the section of the shot core
So you're talking about when the parachute.
when you deploy the?
Okay, so the distance between the parts that separated from the rocket, that's right?
Yeah.
Okay, just let me check the diagram real quick. But we do have a diagram that shows the distance between the parts when the parachutes are deployed. Just let me confirm that data.
Okay. I share. Let me share the screen to show you an example.
Okay. Okay. So this is a quick diagram.
Okay. Okay. Perfect.
Okay, just give me a moment. So it's
I
going to
stop
be
sharing.
3.3
Okay.
meters from the nose cone to the parachute, and then 6.4 meters from.
Okay.
The parachute between parts A and B, is that your drogue parachute or your main?
Joke in me.
Broke, you mean? Yeah. The from the middle tube to the upper one is the drogue, and the main is of the upper one. We have a better diagram here.
Okay. Can I see? Okay. Yeah, but that one only has the total leg of the shot core. You have the distance between the components. Because, for example, my intention is let me show you an example in the
The
screen.
distance from the nose cone to the parachute is 3.3 meters, and from the parachute to the middle tube is 6.4. Then from the middle tube to the drogue parachute is 3.3 meters, and the remaining length of the short core is 6.4.
Okay. Okay. You can see my screen.
Yes.
Okay. You have two events during the recovery of your rocket. Do you mention that you have the drop parachute in the lower iframe, just behind the rocket motor? Yeah.
Yes.
Okay. Then you have this situation. Just to be sure, the leg A of the choke core plus the section B of the rocket is all the rest of the rocket. need to be less than the short course C, just to prevent the heat the components
Okay.
during the high altitude event. Then do you have the whole situation in the rocket? Maybe you can send me a detail diagram after the meeting, but
Okay.
no problem.
Okay, so we're gonna send you the complete diagram to you after the meeting. Okay.
Yeah, thank you.
Okay.
Okay.
Is there any other question?
Yeah. The nose cone deploys at the main parachute, and what is the section that you of the rocket that deploy and separate in the drug? Can you collocate the body tubes at the way that you plan to?
Okay, so this is the motor tube, which is the lower one, and we have the middle one, and this body tube with this one is fixed, and then we have the fiberglass, which is the last one. So the main parachute is going to be deployed at this section, and this is what's going to be separated.
Okay. In that section are the avionics bay?
The So the avionics bay is going to be this middle tube, and the recovery avionics is going to be at the other one.
Okay, and the body tube from fiberglass separate from all the other body tubes?
The fiberglass body tube is going to separate from the middle tube, and also the nose
Okay.
is going to be separating from the fiberglass body tube.
Okay. And sorry, I just want to confirm. The nose cone deploys. That's no problem. But the other section that deploys in the drug is between the fiberglass and carbon fiber tube?
Yes, between the upper tube and the middle tube.
Okay, yeah. Then that body tube is not touched with anything during the descent?
I mean, yeah, there's going to be a short cord that's going to run from the fiberglass body tube until the motor body tube to the centering ring. Well, to the motor tube end.
Okay. Maybe let me change to Spanish to only understand.
Okay.
¿Cuáles son las partes donde se van a separar el cohete?
Las únicas dos partes que se separan es esta, que es del tubo de fibra de carbono, con el de fibra de vidrio, eso se separa, y también el de la ojiva con el de fibra de vidrio.
Ok.
Y estos dos tubos son los que se mantienen fijos durante todo el vuelo.
Ok. Ahí mi pregunta es, ese tubo va a estar volando sin nada atado, ¿no? El tubo de fibra de vidrio.
O sea que detiene la caída, ¿no?
O sea, este tubo en el...
Sí, va a tener el motor y el retenedor.
Ajá, aquí en esta parte se va a poner la cuerda que va a unir esta parte con la parte inferior del rack de recuperación para que se mantenga unido todo.
Ok. No, con eso. Ok. Yeah. Sorry, Robert. I only want to know what is the plan of the team that they plan to attach all the parts and what is the recovery process in each event.
Yeah, and I don't have a clear idea of that either. Do you know which one of those joints is not going to open during flight?
The team mentioned that they wanna use first deploy the nose cone from the fiberglass body tube, and then they say that that fiberglass body tube deploys. The only body tubes that are attached during the descent is the two fiberglass body tubes. But
There's only one fiberglass body tube.
Yeah, the two carbon fiber body tubes are going to remain fixed. The lower one, which is from the motor, and the upper one that has the avionics, the payload. Those two body tubes are going to remain fixed.
So that joint right there, where the gentleman has his hand right now, is not going to separate during flight.
That's correct. Yeah, that's going to remain fixed.
Okay. And at apogee, is the nose cone going to be deployed, or is the nose cone and the upper piece of airframe, the fiberglass airframe, are those being deployed as a unit?
Yes, at the apogee, the nose cone and the fiberglass body tube is going to remain fixed. And at the main deployment, the nose cone is going to pop out to release the main parachute.
Okay. And how will the nose cone be secured to the upper piece of body tube?
It's going to, well, right now we do not have a shoulder on the nose cone, but we are planning to use a coupler that's going to join the nose cone with the fiberglass body tube.
Sure. But you're going to have some way for that coupler to separate, correct?
Yeah, so we're going to be using sharpins so that deployment is done correctly.
Okay. Walter, can I ask him to try something for me real quick?
Yeah.
Guys, can you please lay your pieces of the rocket out on the edge of the stage there in the order that they're going to be in flight?
Okay. ¿Pueden colocar en el escenario horizontalmente? No, horizontalmente.
Lay it out at the spot on the edge of the stage.
En el escenario pueden colocar.
Okay. The floor works too, whichever way is easier.
Okay. Yeah. I have the same question like you, Robert.
Okay, now the piece of the body that you just had your hand on, we're going to call that piece A.
This one A.
That's A. The next one is B. Then the first fiberglass piece is C, and the nose cone is D. Okay?
Okay.
So at apogee, the rocket is going to break between B and C.
That's correct.
Okay. Now C and D are going to be put together with a shoulder that uses shear pins.
Yes.
Okay. Now, you understand that when you separate at apogee between B and C, there's going to be a shock cord that holds them together, correct?
That's correct.
Okay. When that shock cord reaches its maximum length, it's going to stop the pieces from moving apart.
Yes.
Okay. What I'm concerned about, what is difficult to do, is making sure that when that happens and that shock cord gets tight in the air, that shock isn't enough to break the shear pins that hold the nose on, and now all of a sudden you've deployed your main at apogee.
Yeah, actually, we're going to be using the daisy chain technique at the shock cords, so that it doesn't, the cord doesn't feel a jerk when it becomes when it's at its full length.
So you're going to try and use the daisy chain to absorb the shock forces to minimize how hard it's going to pull on that joint when you're at apogee. Okay, fair enough.
Okay, perfect.
Okay, one more question about the lower hard point of the recovery. Do you use something to prevent the shock cord cuts between the edge of the iframe in the end of the B iframe? Because in the recovery, you can control what is the position of the components, but the shot core hits of the edge of the iframe and maybe can cut.
So what we're planning to do is that there's going to be a centering ring inside this body tube, which is the B, and the shock cord is going to run through these holes of the centering ring.
Okay, but now in the center ring is in the end of the iframe, in the edge. No, lo que pregunto es cómo van a prevenir que la cuerda se rompa con el rozamiento del borde del fuselaje.
Va a tener se planea poner como la manta tipo.
We're planning to use the coating to prevent the powder to burn the body tubes. Let me show you the piece that we're going to be putting inside the body tube. This is going to cover the inside of the body tube, and this material is soft, so it's going to help us so the shock cord doesn't rip with the friction.
Okay, and what is the plan to that Nomex be in the edge all the time between the descent and prevent the friction between the edge of the iframe and the shot core?
So you're asking about how we're going to place the Nomex blanket inside of the body tube?
No, guys.
No.
At the end of tube B, where tube B meets tube C,
Okay.
that tube has a hard, sharp edge to it, yes?
Yes.
As the rocket is falling from apogee, there's going to be a cord that comes out of that opening.
Okay.
And it's going to be subject to a lot of abrasion and rubbing against the edge of that tube. I think and Walter, correct me if I'm wrong, man, but I think what Walter is asking is how are you going to protect the shock cord from the edge of your tube B so that it does not abrade it and ultimately cut through it as your rocket comes back down?
Básicamente, o sea, la cuerda cuando salga por aquí va a
Podemos
tener
estar
mucha
que por la
fricción,
fricción
entonces,
se...
¿cómo vamos a-
Sí. Porque el punto de anclaje que tienen ustedes es en el anillo centrador, está bien, va a estar abajo, pero cuando esté tensada la cuerda, va a haber una fuerza rozando pues,
Por ahí.
el borde.
Sí, con lo que le ponemos la protección de fuego, pero que eso va a la
So, well, there's also a coupler between these body tubes, and inside the coupler, we're going to be placing it's kind of like a coating foam that's going to be around the inside of that coupler. So, because the material is soft, there's not going to be a lot of friction between the cord and that point.
But when B and C separate, isn't the coupler going to stay attached to piece C?
When B
What
and
is the coupler?
the coupler, we do not have it yet.
Right.
No, but what is the where do you plan to put that coupler? In the end of the body tube B of the start of the tube C?
Yes, the coupler is
Okay.
going, after separation, the coupler is going to remain at section C.
So then anything that's part of that coupler to provide some shock absorption is not going to help you on the edge of tube B because there's not going to be anything there. Walter, am I understanding what your concern is, right? That it's the edge of tube B that you're concerned about abrading the shock cord?
Yeah.
Okay.
Yeah, I can help the team, but I want to know is they have a plan to this situation.
Is there any recommendation that you can give us so that we can prevent that to happen?
Yeah, some teams maybe use tape in the section of the shot car, but maybe it's not the best idea. I can maybe use a tubing in the electronic store. You can use a tubing. You can maybe set a head to reduce the diameter, and that piece of tubing are in the same place of the short cord and prevent, and maybe you can loop the tubing and prevent the friction.
Okay, perfect.
Robert, do you have any other recommendation for that?
I think probably a piece of garden hose would be a good protector for your tube. And then you could just put a knot in your shot cord above and below it to keep it in place. What some people do, and I know that this might be a little bit harder to figure out, is they will literally get a tennis ball and they will drill a hole in either side of the tennis ball and run their shot cords through it. And they place it just perfectly so that when the shot cord is pulled into place, the tennis ball is right at the edge of the tube on the inside. So any sharpness or anything, the tennis ball holds the shot cord away from the edge of the tube.
Okay, perfect. So,
but a piece of hose is probably easier to do, and it's more forgiving because it's longer than just the 2-inch or a 2.5-inch tennis ball.
okay, perfect. So basically, the idea will be to place the garden hose around the diameter. I mean, inside of the.
No.
You're going to run
shot
your shot cord through your piece of hose.
Okay, perfect. Okay, perfect.
And then lock the hose in place somehow so that when your shot cord is deployed, the edge of your tube is where that piece of hose is, so that the hose is what gets chewed up, not your shot cord.
Okay, perfect. Thank you so much.
No problem. Okay, now about the chirpings, do you mention that you use chirpings? How many and what is the material of the chirpings?
So we are using the nylon sharpens, which are right here. These are the sharpens that we are planning to use, and we are placing 4 of them.
In each separate section?
Yes, on
Okay.
each section that separates.
Okay. Then with the avionics, where is the avionics bay? Or where is the avionics in the location in the rocket?
Hi, my name is Eric. I'm part of the avionics team. For this time, we got a SRAD computer, which is consists in 2 parts. The first part is run by an SP32, which sends telemetry to the ground station. And the second part is run by a Raspberry Pi Pico, which turns on the black folder of the parachutes.
Is this your experimental payload, or is it your flight control avionics?
Yeah, this is the flight control avionics.
And you designed, and both of the avionics are SRADs. You're not using a COTS altimeter.
No, yes, we are using a COTS altimeter.
Okay, where is it?
Okay, so, well, this is our RC3, which is the altimeter that we're going to be using. And this, and you asked where is it at the rocket? At which section?
Yes, which of the joints is going to hold your flight control avionics?
Okay, so this body tube, the fiberglass body tube, is going to have the flight computer. And the avionics, which is the payload, is going to be at this middle one too.
Okay. And first, with the avionics, how do you plan to attach the avionics? There is some coupler, or is in the coupler between the body tube B and C?
So we're gonna be using some rings, some steel rings, on which we're gonna be connecting the CubeSat, so that we can make sure that the CubeSat is gonna be like stable throughout the flight of the rocket.
Okay,
Where
that's for
are
the payload.
Where is your altimeter going to be housed?
The altimeter is going to be housed on the fiberglass body tube.
In a
Where part?
coupler or within the tube itself?
Yes, the altimeter is going to be inside the body tube, not the coupler.
Okay.
How are you going to protect it from the black powder charges if it's going to be in the coupler? Or if it's going to be in the body tube?
Come again? Can you repeat that question?
Yes. When your black powder charges go off, if your altimeter is in the same tube with your black powder charges, the pressure wave from your black powder charge will destroy your altimeter. How are you going to protect your altimeter if it's not in one of the coupler tubes?
Okay. I'm gonna explain you how we're gonna place the altimeter. Basically, we are using a recovery rack that's going to be inside the body tube, and the black powder charges are facing away from each other, and it's going to be protected with this plate.
Okay. Do you have that bulkhead in? Okay. Okay.
Yes, basically. So this is the rack or the bay that we're gonna be using to hold the altimeter. And one of these plates, well, we're gonna be using two of these plates that are gonna be at each of the ends of the rack, and the black powder charges are going to be at the surface. So they're not gonna have contact or are gonna be separated through this plate. The black powder charges.
So why aren't you putting that rack in one of your couplers? Why is it in the body tube instead of in a coupler?
So actually, this rack is going to be attached to the coupler and also a part of the body tube. It's not going to be completely inside of the body tube.
Okay.
I don't understand. Do you, Walter?
Let me ask in Spanish.
Yeah.
Okay. La duda que tenemos aquí es por qué no ponen esa aviónica en el acoplador y por qué en el tubo. O sea, lo que quiere saber Robert y yo es que cómo va a ir insertado, cómo lo van a con tornillos o sujetado dentro del tubo y cómo van a prevenir que la presión de la carga o la combustión de la pólvora dañe las computadoras.
Ok. ¿Te explico primeramente en español?
Sí.
Ok. Es que vamos a utilizar una de estas tapas. Aquí es donde va el acople. Entonces, la tapa va a estar colocada en esta parte. Después vamos a tener una...
Terminando el acoplador.
¿Perdón?
¿Va terminando el acoplador? O...
Estas son las dos tapas.
Sí.
Y el verde es el
A ver, si quieres le mostramos este diagrama.
sí.
Ok.
Este es el cople, el que está en color verde. Y este que estoy señalando aquí es una de las tapas que se está mencionando. Esta es la bahía o el rack de recuperación. Esta es otra tapa. Entonces está entre el tubo, y el rack, el cople, perdón, el verde.
Ok, ok.
Por el espacio que tenemos aquí del paracaídas, por eso no lo bajamos.
Ok, deja la imagen, le voy a explicar a Robert. Robert, this is the open rocket file of the team, but that you see is in the right side, the payload, then in the left, the drop parachute and the shot cord. Then in red, do you see a bulkhead? Then the avionics is in the mouse. The black mouse is the avionics bay. I think so. There are one bulkhead inside the coupler, and then in the left they have another bulkhead and the main parachute. That's no make sense for me, but
Okay, you understand what they're doing?
yeah, but they don't sense. I understand and a half, but no at all. Because I don't know why they don't put the avionics in the coupler. It's more easier. Let me tell. Chicos, la carga útil que tienen ahí está debajo. No ponen, ¿por qué no ponen toda la aviónica en lo que viene siendo el acoplador y bajan lo que viene siendo la carga útil hasta abajo? Lo que pasa aquí es que está la duda de eso, cómo va a salir desplegado, qué se va a quedar en su lugar y la aviónica, cómo se va a mantener en su lugar, porque tienen un bulkhead del diámetro del fuselaje interno y luego tiene otro bulkhead debajo de la aviónica del diámetro interno del acoplador.
Sí.
Pues sí.
Sí, porque una parte va en el acoplador y otra en el tubo del fuselaje.
Ese acoplador va pegado con epóxico en la parte, en el fuselaje superior, en medio, ¿no?
Con tornillos en la parte superior y con shear pins en la parte inferior.
Okay, Robert. This is the situation. They use the coupler, but they don't use the coupler like avionics bay in a half. The upper bulkhead of the avionics is they have the diameter of the internal iframe. The forward bulkhead is the diameter of the internal coupler, and they use that section of the rocket for the avionics because they know they don't have enough space for the payload and the drop parachute and the shot cord. They don't have already finished the rocket. I recommend that they can maybe a change for this one.
If they have the time to, I would also agree. May I ask a question?
Yeah.
The bulkhead that is going to separate the electronics from its charge, the one you had in your hand earlier. May I see it for a moment, please? Yes.
Okay.
How is that going to be glued into place inside the airframe, or is that going to slide in and out?
Well,
¿Va a estar pegado o va a estar?
Va atornillado también al fuselaje, como los
They use screws to attach that bulkhead.
Pero dos capas, no de shear pin.
And what is it going to be attached to?
Okay.
o sea, esto va a estar atornillado en el tubo del fuselaje.
Ajá, las dos placas.
Both of the bulkheads are going to be screwed into the airframe.
How are you going to screw that thin piece of material into the airframe? There's no thickness there to attach a bolt to. How are you going to screw it in place?
¿Estas son las placas que vamos a usar o van a ser más?
Van a ser más gruesas.
Okay, so actually the bulkhead that we're showing you right now is not the one that we're going to be using actually, because the one that we're going to be using is going to be thicker so that we have enough space. Actually, the bulkhead that we're going to be using is going to be this thickness. It's going to have this thickness.
Okay. Walter, are you comfortable with their plan? Because ultimately, it's your call to make here.
Yeah, not at all. I need to see the physical components to see maybe the best option. But right now, they don't have yet the component. The idea can work, but they have too many risk to piloter. It's not conventional design. Maybe I can review the design with the team before the meeting to make maybe a better option.
Actually,
Because they have yeah.
no, I'm sorry. I was going to tell you that we were talking, and I think that there's an option that we can put the payload below. I mean, we can put it down so that we can put the altimeter rack in the coupler and not between the coupler and the body tube to make it.
Yeah, but what is the actual stability value that you have in the rocket? Because you put down the payload more than the location, you can maybe has less stability.
Right now, our stability margin is 2.13. So if we lower the payload, we can. The most probable thing to happen is that we're still going to have enough stability.
That's the simulate stability, okay? And what is the percent of error that you have between the simulation and the physical rocket? All the weight of the components that you have in the rocket are the same?
So far, all of the weights of the parts of the open rocket are the real ones. The weight of the body tubes, of the nose cone, of the bulkheads. I mean, most of the components of the open rocket are has the real weight.
Okay, yeah, because for example, in that open rocket file, do you have in the design? Sorry, do you have enough space in front of the rocket motor to put the payload, and that iframes, the A and B iframes don't separate in any moment during the recovery. You can maybe load the payload, and now you do have enough space to put the
Recovery.
uh, the recovery, the main, and the drop parachute, and use the coupler like avionics bay.
Okay, perfect. Yeah, of course we're gonna be doing that. You're talking about that we have enough space between the motor tube and the middle tube. I mean the A and B body tubes, so that we can lower the payload, and we have enough space to put the recovery rack inside the coupler. Is that correct?
Yeah.
Yes, and then your drogue parachute goes into the space at the top of tube B, and your main would be up at where your nose cone and just where it is now. But then you can slide all of your avionics down into your coupler tube between B and C.
Okay, perfect. That's
Yeah,
great.
if you make the updates, and maybe you can send to us the update file and check
Okay.
to have the final design. You have enough time maybe to make a change, and you didn't make all the rocket assemble.
Yeah, actually, that was one of the reasons why we still do not place the centering rings and those components inside of the rocket, because we wanted to make sure that we were doing it the best way possible. But given the situation, the best thing to do is to modify the design so that we can fit the things in a better way.
Okay.
So as soon as we modify the design, we will send it to you.
Okay, thanks. And if you have any question about the recommendation, just tell us, and we can help you.
Thank you so much. We really appreciate it.
Okay. Now maybe we can pass with the type of deployment. Do you plan to use black powder? How many grams? And do you have the container that you use to?
Our drop parachute will have 4 grams, and as backup 5 grams, and our main parachute will have 6 grams, and as a backup 7 grams. This according to our simulating calculus.
Okay, and do you plan to make the ground deployment test in the competition or before the competition?
In the competition.
Okay.
Both. I'm sorry. Both. We will do both tests.
Okay. Okay, thanks. That's the container for the deployment chart. Okay. Okay, thanks. About the hardware, what is the dimension material of the eyeballs, quick links that you use in the recovery section?
So the materials of the U-bolts and the quick links are steel.
Okay.
And that is the quick connector.
Okay. Okay.
And how are you connecting your shock cords to the rocket itself?
Conectar las cuerdas de choque al cohete. Pero ¿a qué componente?
Do you have the bulkhead with the U-bolt?
Okay. So one of the quick connectors is going to be attached to this U-bolt.
But you're not using that U-bolt, correct? You're using a different piece.
Yes, that's correct.
But it's going to have the same type of assembly in the one you're actually going to use?
That's correct.
Okay.
Okay.
So at some point, bring back that bulkhead that you were just showing us.
Okay.
That hole in the center of the bulkhead, underneath the U-bolt, that is where your wires run for your deployment charges?
Aquí salen los cables para las cargas. Sí. Yes, the wires go through this hole, and then the capsules with the black powder are going to be placed in here.
Sure. How are you going to plug up that hole once the wires are in it so that the deployment charge doesn't leak back into the avionics bay?
You're saying that how are we going to seal this hole?
Yes.
Mhm.
We're going to be using epoxy to seal that.
Okay, but
How will you use epoxy to do that?
I mean, after we take out the wires, we're going to place epoxy around the cable so that there's no leak of black powder.
And are those wires going to be permanent then, or are you going to have to remove them for a second flight?
Yeah, actually, we are going to be using these quick connectors. So the wires run from the hole to this quick connector, so the wires remain fixed. And then
Okay, now I understand.
Yes, and then the other end of the quick connector, that's the
Will
one that's going
connect
to
in
be
there. Right. Okay, I'm with you now.
Okay,
yeah,
perfect.
that's fine. Okay. About the rocket motor, you already purchased the rocket motor? Do you already have? That's the casing that you plan to use in the competition?
Come again, I'm sorry?
About the rocket motor, that casing do you have in the video is the same that you plan to use in the competition?
No, this casing is for the M1845 motor, but this year we're going to be using an M1939, but we bought the casing and the propellant from Wildman Rocketry, and it's going to be delivered at the competition.
Okay, perfect. Okay. Now, maybe the payload. Can you the payload? It is. What is the payload that you use? Is it only a mass, or do you have electronic?
Yes, we're going to be using an inner payload. We're just going to be placing this CubeSat inside as a payload, but it is not going to have any avionics inside of it.
Okay. And what is the plan to attach that payload to the body tube?
We're going to be using the centering rings to hold the payload. It's going to be placed one at each end, and the centering ring is going to be attached to the airframe using bolts.
Okay. How many bolts and the material is the same? Stainless steel?
Yes, we're going to be using a stainless steel, and they're going to have 3 bolts.
Okay. Okay, thanks. One more thing about the avionics, about the batteries. What type of batteries do you plan to use in the avionics?
We are using 2 9-volt batteries.
Okay.
Alkaline batteries. We're going to be using 2 9-volt batteries.
Okay. And now about the switch. How many switch and where do you plan to do you have external access for the switch to turn on the avionics?
Yes. We're going to be using 2 switches we're going to have access from the body tube, just like we are doing with the nose cone. That we have an external switch. That's what we're going to be doing for the avionics. We're going to place the switches so that we can access through the body tube.
Okay. One more thing about the avionics. If we update the design and use the coupler like avionics bay, do you plan to use a switch band?
A switch band?
Yeah, maybe they can be a good option because do you need to make a venting holes for the avionics?
Okay. Yes, I mean the plan is to place the vent holes on the upper tube. Is that your question? I'm sorry.
Yeah. Right now with the actual design, the plan is to make the venting holes for the avionics into the body tube?
Yes.
Okay. But in the plan that you update the design and put the avionics in the avionics bay in the coupler, what is the plan? Do you use a switch band?
Switch band.
La banda, hablo de ¿van a poner alguna banda para el switch? This is a recommendation and a question because if you use the coupler like avionics bay, maybe the best option is to put a switch band to have the switch in that location, and in the same location have the venting hole for the avionics, and don't make the venting holes in the body tube.
Okay. So basically use the holes that we're going to be using for the switches, also for the vent holes?
Yeah.
Okay. Yeah, we can do that.
Yeah, I can help if you need help. But yeah, maybe that can be a good option.
Okay.
Guys, I apologize. I have another meeting at 7:00. I need to get off I need to move on to. Please know that if you have any questions throughout the rest of your time, if you want to contact me, I'm happy to help you with your design changes or anything I can do to help you with the process along. I think, Walter, you're going to reply in at the end of the session regarding the video review?
Yeah.
Okay, then I will leave you guys to it, and hopefully, I think you're in a good place. You just need to get further on with your build. And if you have any questions or there's anything I can do to help, please don't hesitate to ask me, okay?
Thank you so much.
Thanks, Robert.
Have a good night, guys. Bye-bye.
Okay. Voy a parar la grabación.